Okay, welcome all to NOVUM Open House Event. I will be the facilitator or moderator also for this event today. My name is Alina Ruonala-Lindgren. I work at VTT as a co-creation manager in the area of biomaterials, but today I will be your host. So welcome all. Welcome all to also those who are participating online. So please have a seat all and we can start with the program, which is very exciting. And obviously after the COVID situation, it's exciting to meet you all face to face, even wearing masks. So we're all wearing masks, others those that are giving presentations. So I'm so happy to see you here. So for all of you to know, so this event will be recorded and the recording will be sent to the participants and also available online. There is a chat opportunity for online participants to ask questions, and for those who are present here, I ask you to wait for the microphone, since we want obviously to give your question also to the online participants. So Anastasia, who is there taking photos, so she will have a mic and she will bring it to you if you have a question that you want to pose to the presenter. And for the presenters, I'm also one of my important tasks today is to keep track of time. So when your time slot is ending, so I will be standing there and getting closer to you. And if I'm really standing close to you or next to you, then you know that your time is up. So that is a hint for you to start closing your presentation. We will go through the program. You have all received it beforehand. And for those who are present here, just a note that after the streaming and the presentations ends, so we will have lunch in the same building, in the same floor as this is. But we will come back to this after the presentations are over. And obviously after the lunch, the program will continue, and we hope that all of you will join us to get to know the pilot line, which is brand new. It was open in February and now up and running in close by walking distance from these buildings, and we will move to that facility after the lunch. We will come here and meet here and leave from this place. So I think that is all from my side, and I will actually now give the floor to the first presenter, who is Heli Kangas. She's the NOVUM project coordinator, and she comes from VTT, but she will tell you more about the project itself. So welcome, Heli.
Thank you, Alina, for the kind introduction, and welcome all of you in person in this room and also online. I'm very happy to be here, and I'm very happy that you are here in person and online. As Alina already said, my name is Heli Kangas, and I work as a technology manager at VTT, but today I'm here as a NOVUM coordinator. And I will tell you shortly what is NOVUM. So NOVUM acronym and the long title for this project is a pilot line based on novel manufacturing technologies for cellulose-based electrical insulation components. But as you will hear soon, NOVUM is much more than that. But it's a project funded by European Commission, European Union, under the Horizon 2020 program and the Spire public partnership. And the total duration of NOVUM is 4.5 years, and we are currently on the last month. So this means that NOVUM will end of March this year. And NOVUM partners are 9 from 5 European countries. So there is VTT, Technology Research Center of Finland, and that is the Novum coordinator. And VTT is also involved in the cellulose material development and also testing of the 3D printing of additive manufacturing. Then we have a printer, which is a local SME, and they are being involved in the 3D printer development within Novum. Then we have ABS from Poland, and ABS is responsible of designing and developing and putting together the actual post-processing line of Novum, which you will, of the pilot line, which you will see today. And you can, those of you online, you will see a short video on the Novum pilot line. Then we have JRS from Germany, and JRS is our material supplier, so they have been supplying us with the microcellulose that we used in our cellulose composites. Arditech from France is the partner who is providing for us the life cycle assessment, life cycle calculation, very important things in this context. AGH, it's a university from Poland, and they have been involved in testing of the electrical insulation components. And then we have the end-use partners. So we have Hitachi Energy involved in electrical insulation components, CRF, which is the Central Research Fiat, so that's the automotive partner. And then we have Meyer Turku, which is also local from here, Turku obviously, and they are involved in shipbuilding. So these are the end-use partners. And where did it all start? So it started with an idea from ABB, which is currently Hitachi Energy. They had an idea that they wanted their electrical insulation component manufacturing to be more streamlined, more energy efficient, more automated, and so forth. And they had this brilliant idea that why not use 3D printing to do that? So they contacted VTT because we had some background in development of cellulose-based materials for additive manufacturing or 3D printing. And together we started to put together this project and contact the partners that we considered relevant for this purpose. And the inspiration was that this ABB's 11-step manufacturing method could be streamlined into just maybe 3 steps. But then after it's been 4.5 years, so things have changed. And now, as I said, Novum is so much more than just electrical insulation components. So we are today focusing on 3D printing of cellulose-based materials. There is cellulose-based composite, and then we are also looking into 3D printing of fiber foams. And then we have the 3 different end-use cases. So we still have the electrical insulation components represented by Hitachi Energy, but we also look into automotive components represented by Central Research Fiat, and then we also look into decorative elements in cruise ships, which is represented by Meyer Turku. And as I said, 3D printing of fiber foams is also there, for example, for insulation purposes. And then the real focus and the outcome needs to be this pilot line, so that it has been designed and built up, and that's based on 3D printing technology. So this is the focus of Novum today. And you will hear about these different components of the Novum project in the following presentation from the project partners. But at this point, I would like to thank you, and once again, very welcome to this event. Thank you.
Thanks, Heli. We'll move on to the next presentation. I ask Tomi Kalpio from Printer to come to the stage, and he will tell about the pilot line totally, and also showing you this is the grand premiere for Novum pilot line video. So Tomi will show you also that one. So welcome, Tomi.
Thank you. Can you hear me loud and clear? Welcome all of you from my behalf as well. It's finally nice to meet you face to face after a while. Last time I was in this big audience in Formnext last November, so it's nice to be here again. Today I'm telling you quite shortly, around 10 minutes, a little bit about the history of this pilot line, how the development has been gone through, and some ideas about the future. So hoping that we can get some discussions ongoing about the future manufacturing of hybrid manufacturing, more specific to be. So, like said, I would like to have some good discussions after this presentation next to the pilot line or in the lunch. So we don't have much time for the questions right after my presentation, but later on we will have a lot. Some showcasing of these future modular environments. So not only the printer itself is modular, but the environment where it will be used in production lines can be also modular. Like I see that this is more future than these lines that are meant for only one purpose at a time. This is divided into two parts. So first regarding the printer itself and the modularity. How it all began. Heli already told you a little bit about how it has been evolving these projects during these 4.5 years. So at some point we have had some changes in the focus areas. So that's why the focus of this development part has been also changed a little bit. So in the left side you can see where we started with small desktop unit. We started printing some base type of cellulose materials to make some pre-analyses. And in the next phase, we developed this small-scale granulate printing system, which was already usable in the production lines as well. Like you can see in the middle top picture, there's a conveyor on bottom side of this desktop unit.
You can move here. I was asked you to stand here
so you can see me.
Online people can see you as well. So
Okay.
Sorry.
But like I said, there's a conveyor unit on the bottom side of this desktop unit. So you can move the pallet in, lift it up, print it on top of that, and take it out automatically. But this was still on the small scale system. But in this phase, we got a small change to the project. Like you can see, the plan was to scale the concept a little bit bigger. Like you can see on the right side, the end product that you will see soon in a couple of hours in the pilot line, it's a little bit bigger than in the middle scene. So in this middle picture, it was like 300 millimeters times 200 millimeters times maximum 500 millimeters if you use this lift system on the bottom of this desktop unit. So now it's 2 meters times 5 meters times 1 meter. That is the maximum build size of the machine. So it was a quite challenge for us. We decided to take it, and now we are quite happy about it. So we have a very nice platform that can be used in the R&D, and why not in some production systems as well, or production parts. And also it's very scalable to the different challenges in the future from the modularity point of view. So both of the machines are very, very modular from that point of view, that you can use whatever tools or printing heads with the machine you want. Few keywords. We can use our own developed printing heads, tools, component placement units, quality control systems, and so on, but also integrate third-party printing heads or tools in the same machine in the future based on the end product needs. So it brings us some possibilities to find new kind of use cases, including multi-material. And this is one good example that I will come a little bit later on. So combining, for an example, this cellulose-based material as a solid part and then fill it up with the foam, for an example. These are very interesting cases for the future as well, using different kind of materials in both cases. Process is fully automated, so most of the 3D printing systems are something like that. You will open the door and take the parts out, and then you put the new printing plate in and again start the printing. But In this system, it's fully automated. So again, pallet comes in automatically. When the print job is done, it takes it automatically out. So it minimizes the downtime of the printer and manual labor work as well. Different kind of analysis, laser measurement systems, calibrating the printing bed, couple of cameras to follow up the process, and also thermal camera, which was quite recently integrated to the system, which helps our future development both in the process side but also material development side, so we can see that the flows and everything are correct and the temperatures are where we need. And again, in the bottom side, you can see this automatic interface that enables us to use whatever printing heads or tools with the, so to speak, printer. Couple of keywords. Printer as a name comes from biomaterials and bioinks plus 3D printing. If you didn't know that, now you know. Sustainable manufacturing. In this case, in the NOVUM project, it means that we have been using biomaterials and recycled the same material locally multiple times and made some tests as well, and it seems to work quite well. And of course, the possibility to use industrial grade standard materials with the same machine, also recycled versions. And multi-material is one of the key aspects like shown here. So we can have up to 4 different materials or even some component placement systems, which could be something that we can also implement some sensors inside of the parts, printed parts, which could be quite interesting as well. Like mentioned in the bottom side, you can see these few development ideas, which component placement and this multi-material thing is one of the key aspects and main focuses, at least for us, including the foam. And the second part is related to the pilot line and modular hybrid manufacturing environment. There's a lot of text. I'm not going through all of these. You will get the slides later on. I just wrote down all the main aspects that, or topics that is interesting, at least from our point of view. But the main thing is that the whole production line should be modular and not only the 3D printer itself. We can then have a multiple 3D printers feeding the same post-processing line, which could be very important with bigger parts when the printer itself is the bottleneck of the production. So if it takes multiple hours to print some parts, the other part of the production line just waits the parts. So then we can have a multiple printers to print the parts to speed that part up. But also hybrid manufacturing environments, so that we could have injection molding machines and 3D printers in the same production lines, so that the both manufacturing machines feeds the same post-processing line, even in the different phases of the product life cycle. For an example, in the ramp-up of prototype phase, we could print the parts and mass produce them with injection molding machines, and later on, after the mass production phase is gone and we have a, so to speak, spare part phase, then we could also again move that specific part to the 3D printing processes or combine those together, so using injection molded part as a base and insert some sensors on top of that and print another material on top of the injection molded part. So all kind of ideas are something that we have been thought about and in the future that could be utilized to use the best practices from all the different manufacturing methods. Here you can see the NOVUM pilot line, and we will have shortly a better video about it, so it gives you a better idea about the concept, and also I hope that everybody comes after this lunch to see the real line in the Machine Technology Center, which is quite close, a few hundred meters from here. But it starts from the left with the printer, where the part is printed, then it moves with the pallet to the input conveyor, and then the robot takes it from the pallet and takes it to the vision station and post-processing line for further processing. And there could be multiple different kind of processes like drilling the holes or polishing or all kind of different methods based on the needs. Here I added some 4 different case examples that I talked about earlier about this modular system. So the same post-processing line could handle, for example, parts from printer and injection molding machine. There could be also multiple different 3D printers feeding the same post-processing line. Or this case that I mentioned, that injection molded parts will be moved to the printer and it will be, for example, placed some sensors on top of that and printed some other material on top of that or something like that. So just to raise some ideas that you can take home and think it through later on if you get some good end application ideas. And this is the little bit similar case that I mentioned. So first print granulates, for example, in the first machine. Then next one place components and third one print foam. And all of these can be made with some same machine or machines which is next to each others as well to speed up the process if needed. I don't say thank you yet. I ask if you could put the video on. Thank you.
In the fast-moving world of today, how can we replace the inefficient, labor-intensive and rigid processes of yesterday with new and better ones? We have the answer. The NOVUM project has created a one-of-a-kind pilot line that combines the benefits of versatile cellulose-based materials, flexible 3D printing and a fully automated post-processing line. This first-in-the-world pilot line enables rapid, design-driven production of intricate components for various end uses, such as components for electrical insulation or for the automotive and shipbuilding industries. The pilot line blends the various, at times complex, manufacturing processes into one seamless stage, and the resulting time and cost savings are significant. The fully automated pilot line is modular, flexible, and easy to scale up. There's no need for manual work, so the risk for human errors is reduced. Our cellulose-based components begin their journey through the 12-meter-long production line from the 3D printer. The revolutionary industrial printer, manufactured by Brinter, is custom-designed and fully automated. Uniquely, the printer supports the future use of a wide range of raw materials, from liquids to solids. The process of exchanging the print head or other tools is fully automated. Materials, print quality, or even the composition can be changed or mixed mid-print. When the printer's ready, a robot automatically fetches the component to the belt. On the belt, the component either passes through a vision station for quality control or moves directly for further processing. At the vision station, faulty components are removed from the belt. Flawless components are cleared to continue to the machining station. The machining station is where the robots rule. They fetch and attach the needed parts to the modular products line independently. The tool-changing interface enables the attachment of basically any instrument. The robots are able to wield tools such as saws, drills or milling heads, or quality control instruments such as cameras or measuring devices. At the machining station, the components get their final form. The station is protected by plexiglass so the robots can get on with their work undisturbed. This unique production line enables large-scale, flexible manufacturing. The integrated and fully automated post-production line saves time and money as the components can be finalized in the same process. Using the pilot line, we can manufacture anything from very small components to parts over 1.5 meters in length. The line is easy to scale up by adding more printers or post-production units to increase the production volume substantially. At the moment, we are manufacturing components for the transformer, automotive and shipbuilding industries. But thanks to the versatile nature of our raw materials and the flexibility of the 3D printing and post-production technologies, there are no limits to what we can do.
Wow, that was something.
Thank you.
Thanks.
Yeah. I also saw
Tommy.
the first time the latest version, so Looks good.
Hey, now it's time to, you can ask questions also, we have some time, so if you have any questions from the audience, so please raise a hand and Anastasia will bring you the microphone. And also for those who are online, so there's a chat, you can post your questions there. I have a question, Tommy. How do you feel now after 4.5 years and it's there in the premises running, up and running? How do you feel?
Quite happy about it. I don't remember much. But it has been quite fast, the 4.5 years, I have to say, but I'm happy that we took the challenge to scale the concept up and we are now in this situation. So I see a lot of future possibilities in this kind of concept and in this with these partners that we have and will have in the future.
Okay. Any technical questions or detail? There's a hand up in the back of the audience, so you will wait for once you get the microphone so you can ask.
Okay, thank you so much for your presentation. I think this is a really great idea. So the question that I have is related to the quality of the surface of the printing. Based on the video, at least I saw that there is some problems, especially at the edge when you are printing. So it seems that the quality of the edge, I would say they are not that much like good, at least based on my understanding. So I think you are addressing those issues by the post-processing. So have you considered any like addressing those issues by the printing process itself?
Yeah, I think the development has been since the very beginning quite versatile. So while we have been developing this printing machine itself, we have been developing these printing heads at the same time when we have been developing together with VTT new materials. So it has been quite challenging to keep up with all these aspects. So there is some development in all of these still, but also it depends, of course, what kind of speed we are using with the printer, what sizes of the nozzle we are using, and so on and so on. So there's multiple variations to affect the quality of the part or surface, depending on the end application. So we have 3 different partners in this project, and they all have totally different types of needs for the quality. And 2 of these cases are something that we will never have an end part directly from printer. So it needs post-processing or some kind of coatings anyway. So it depends what is needed.
Have you considered like print process parameter optimization for those like quality surface?
Yes, of course, and it has been ongoing task during the past 1 year. So it continues.
What would you say is the most challenge that you have faced during this project?
Not say challenge, but it takes a lot of time when we make a lot of tests with the printing head, and then we give the feedback to the VTT who modifies the material, and then we again test. So it takes a lot of time to find the right parameters for both of the aspects, so new material and new technology. So if we would have a ready material that is on the markets and tested, then we would have been to concentrate only the technology development. But now it's like parallel task, so that has been quite challenging. And
so I think I don't want to take too much time.
Yeah,
Let's have a
I think we need to
during
move on.
lunch or
Yeah.
somewhere like there. All right, thank you.
Thank you. A comment from the chat is for Tomi, vaikuttavaa, which is impressive in English, so from Eve Saarikoski. So that is a message you get from the audience online.
Greetings, Eve.
So thank you. Thank you, Tomi. I think we need to move on with the program, so I will move to the next presenter and introduce her. So welcome Kirsi Immonen. She's a senior scientist at VTT and has been working with the NOVUM material, and now she will tell about the material and where we are. Thank you.
Thank you. So good morning, everybody. So my name is Kirsi Immonen, senior scientist at VTT. And together with our NOVUM material development team presented here, we have been developing this novel thermoplastic cellulose-based composite material. And now we are, let's say, going back to the basics, where Tommy presented also what happens to the material. And now we are in the phase where we actually develop the material. And first, I would like to show you a little bit a bigger picture of the soft materials. And actually there is going kind of a transition of these moldable materials from fossil-based original material to the more bio-based materials. And if we think of the NOVUM scopes, we work with these cellulose esters and cellulose materials. Those are located, as you can see, in the world of materials. And if we think of these 3D printable materials for the future, there is actually need for these novel thermoplastic filaments and granular useful for 3D printing, for example, in home use. And then we turn up into the issue that the material needs to be very safe. So no toxic fumes are allowed to release during the printing. And materials need to be bio-based and maybe contain some fibers to bring some stiffness and possibly visual outlook for the product. And we need to consider also the product end of life. So they need to be recyclable, maybe in some case biodegradable, but anyway they need to be have combustibility without fossil carbon dioxide. So maybe one perspective in the future will be like all cellulose composite materials. Then why cellulose in this NOVUM project? Actually, cellulose is the most abundant available raw material. Can be gained from wood, various plants, and also in the form of side streams from agriculture, for example. It is not regarded to compete with food production, can be modified to be thermally moldable. And for example, cellulose esters are actually the oldest man-made thermoplastic materials, having advantages like transparency, dimensional and thermal stability, UV stability, high stiffness and electrical insulation. There are both biodegradable materials, but very durable materials within these cellulose esters. Okay, there are some land use related issues, but those are, let's say, connected with all bio-based materials. And if you think of these cellulose esters, they typically need a plasticizer to adjust the thermoplastic properties, which is a little bit drawback. But for that, VTT has actually developed a thermocell material, which is an internally plasticized cellulose esters where the plasticizer is connected or coupled to the cellulose backbone. So there is no need for additional plasticizer. And more you can read about that, for example, in our publications. Then, aim at thermoplastic novel material development. It was to find cellulose-based raw materials for sustainable additives for manufacturing of material focused mainly on electrical insulation, as Heli already told. So currently, cellulose is very common raw material for electrical insulation. It is usually applied as wet sheets of electrotechnical paper. And as Heli presented, there are several issues related to those processing methods, like the manufacturing process is very complex, consisting multiple stages, takes long time, consumes a lot of energy, and is very labor intensive and results in significant material waste. So there is actually a need for cellulose-based material suitable for 3D printing or thermally moldable, for example, using injection molding. And about the material development, this was already discussed a little bit, but within the NOVUM project, we made the material development in joint collaboration with material formulation, 3D printing, testing, and the prototyping, the final test product and testing them. So it was like a collaborate, simultaneous loop of development. Here is some overview for the material formulation. This new NOVUM material combines a thermoplastic cellulose matrix with microcellulose and bio-based additives like plasticizer and coupling agents. These component manufactured, prototypes are manufactured with granular printing, filament printing, and injection molding. And during the material formulations, also the circular economic considerations were like included. Then a bit overview for the selected novel materials we have developed here. And we see actually 3 different material base material properties here. And one of them is containing this VTT thermocell additive also. And if we compare to those materials to the like commercial 20% fiber containing compounds, mainly containing PLA or BHB or something like those as a base material, we can see that in all materials the mechanical properties are, let's say, more tailorable. Tensile stress it can be a little bit higher value than the commercial materials. Also, the impact strength a little bit higher value than commercial materials. But the most important is that the HDT or the thermal resistance is in a higher level than commercial materials. And then there was mentioned also recyclability of this material, which is a very, very important issue in material tailoring point of view. And we have studied the recyclability of these new materials and find out that it can actually withstand 5 recycling rounds without adding any virgin material. You can see some injection molded samples and 3D printed samples here within the different recycling rounds, that there is a little bit color change, mainly coming from the microcellulose, but not too much perhaps. And even though the color is anyway quite light beige, but still it is called usable within after 5/5 recycling rounds. More you can read from our recently published article. Then if we take a closer look to the recyclability, you can see here the relative change, what recycling causes. There's an increase in tensile strength properties, impact strength properties. Modulus stays a little bit kind of the same level, so small increase in HDT. And we can say that as more as you recycle the material, the actual better properties you get, at least with the injection molded materials. This is mainly due to the homogenization of the material and improved flowability. And as conclusion, we can say that we have developed within this NOVUM project a novel thermoplastic high cellulose content thermoplastic material and demonstrated it successfully in granular 3D printing, filament 3D printing, and injection molding. It has higher strength and thermal resistance than comparable commercial materials. The NOVUM compound is recyclable at least 5 times without adding virgin material. And when used this novel granular printing method, no additional filament manufacturing is actually needed in between recycling rounds. It has natural light beige color, but can be easily colored, as you can see here in this orange boat below. It has soft wood-like touch feel, and on the upper picture you can see a lamp shade where the light is nicely coming through the printed printed lampshade lines here. Thank you. That was all about
Excellent.
material development in NOVUM.
Thank you, Kirsi. Any questions for Kirsi? Yes, there is one. I will look at the chat if there comes anything pops
Okay,
up. But
yeah.
now
Good morning, everyone. My name is Gaurav Das. I am technology manager for Renote with my colleague, of course, Rika Danielsson. I have a question. For instance, we also work in 3D printing, but with different materials. One question is, cellulose, in my understanding, may not be thermoplastic by nature. So I'm curious, because I studied cellulose in Aalto quite a bit, and how did you guys make it thermoplastic? I mean, just in a very short.
You mean this VTT thermocell internal
Yes,
plasticide?
yes.
It's
For instance, yeah.
it is actually cellulose ester having very long aliphatic chains.
Aliphatic chains,
Yes,
okay.
so there's like a plasticizer is actually coupled to the cellulose backbone, which makes it in like thermoplastic itself.
What is the nature of that plasticizer, let's say chemically, for instance?
They can be like a bio-based fatty acid.
Fatty acids, okay.
systems,
Okay, that's
yeah.
all I had. Thank you.
Yeah.
thank you, and you can continue the discussions over lunch
Yes,
also. So that is
of
a
course.
wonderful opportunity now that we are all here. So I think there are no comments from the chat. I thank you, Kirsi. Thank you for the presentation, and I will introduce the next speaker, Leo Staccioli from Arditech, and he will tell about the project's impact in different ways and angles. So welcome, Leo.
Thank you, Alina. Good morning, everyone. My name is Leo Staccioli. I'm from the Arditech Association. We're based in Nice, in south of France. And today I will present some of the results we got from the sustainable assessments. So first of all, this is the process we wanted to assess from an environmental, economic, and social point of view. So basically, we divided it in 4 main steps. First of all, we have the material formulation. Then we have the 3D printing and injection molding. Then the prototype line, and finally the use phase and the end of life. So let's start with the environmental assessment. In this slide, as you can see, we try to first establish a comparison for the production of 1 kilogram of different materials, including NOVUM 28, of course, that you can see on yellow on the left. And for the comparison, we choose different materials, common materials widely used in the industry. So we have polypropylene, polyethylene, and acrylonitrile butadiene styrene, let's say ABS. And what we can say about this slide is that we observe optimized results considering fossil depletion and climate change. If we take, for example, the fossil depletion, we observe an impact reduction up to 60% between our material, NOVUM 28, and the ABS. So these are quite encouraging results. Then we also compared the environmental impact for 3 processes to produce 1 square meter of the same end product, which was a ship counterbar, normally developed by Meiyotoku. So we have 3 processes on these 2 figures. So the first one on the left is our process, the NOVUM 28 material formulation plus the 3D printing of printer. And then for the second and third processes, they're developed by Meiyotoku using hand lamination with 2 different mixes of material. So the first one in the middle is a mix of gypsum and glass fiber, and the second one is a mix of polyester and glass fiber. So they're both using hand lamination. And we can see that the figures speak for themselves. We have really good results concerning our process using 3D printing and cellulose-based material. We have a reduction of 79% in the CO2 emission and a reduction of 90% in fossil resources. And then we did exactly the same thing, but this time comparing a second end product, which is 1 square meter of a car dashboard. And this time we use injection molding for both processes, but using different materials. So we have the ABS material on the left and our material, Novum 28, on the right. And these are quite good results as well. This is not as impressive as the previous scenario, but we can still observe a reduction of 7% in CO2 emission and a reduction of almost half of fossil resources for the same product and different materials. So then we move to the economic assessment. So as for the environmental assessment, we consider 3 scenarios. So the first one is considering only the material formulation with 90% of Brinter's production capacity. Then we consider second scenario with the material formulation and the 3D printing of Brinter, but this time we consider only 2% of Brinter's VTT production capacity. We took 2% because VTT is able to produce 250 tons a year of Novum 28, when Brinter can print 5,000 kilograms a year. So it didn't make sense to allocate the whole production of VTT to Brinter. And the third scenario, we applied the same logic with the 8% of the VTT's production capacity, considering the material formulation and another process, which is injection molding. So these are the 3 scenarios. And then this is just a parenthesis concerning the CapEx and OpEx distribution of the second scenario, which is the material formulation and the 3D printing. So we can see that the OpEx accounts for 63%, the CapEx 23%, and the consumption OpEx 14%. Then if we go deeper in the CapEx distribution, we can see that the machinery of Brinter and ABS are the main contributors, let's say. And for the OpEx, we can see that more than 3/4 are coming from the labor force of ABS, Brinter, and VTT. So this was just a parenthesis. Now I go back to the different scenarios and their results. So for the scenario number 1, we can see that, so considering only the printable material, we try to compare our material with the current printable material on the market. And we can see that we have some really good results with one of the cheapest printable material on the market, around 10 euros. Then if we compare it with nylon filament, for example, it almost reaches 100 euros. So this is quite good. Then for the scenario number 2, we have the Novum 28 3D printed versus the molded gypsum fiberglass and molded polyester and fiberglass. So there are the 2 scenarios that I described previously developed by Meyer Toku. So we can see that our process is quite good, with reaching 70 euros for the ship counter. Sorry, can I have a glass of water? I have a pretty dry throat. Thanks. Sorry about that. So we can see that if we consider only the material, we are quite stable. We have almost the same price for the 3 materials. So considering the polyester and the fiberglasses, the gypsum and the fiberglasses, and all material, it's quite the same. But then if we consider the process itself, the 3D printing, it's a bit higher for us, which is normal because it's a prototype, so it needs to be further optimized. And then we did the same for the injection molding of Novum 28 versus the ABS. So this time we have the ABS, which is quite cheaper. So it's normal because it's a widely used material in the industry. And so our material is a bit more expensive, but the process is the same, which is injection molding. So then we have a first scenario with a huge volume production of 250 tons of Novum 28. We try to forecast. We try to make a business model. So we have a material costing 10 euros, and if we sell it to 12 euros, we can reach a return on investment close to 10%, which is quite interesting. Then for this second scenario, including 3D printing as the process, so of course the price is higher. It costs us around 65 euros, and if we sell it to 82 euros a kilogram, we have a return on investment of 2%. I'm going quick, sorry, Alina. So then we move to the social assessment quickly. This is the methodology we applied. We have the step 1, the goal, scope, and definition. Then we proceed to stakeholder analysis, where we perform different interviews with the different partners, etc. And then we have a product comparison, and all these steps together, we can produce a stakeholder engagement plan and provide some recommendation. Quickly, this is a tool we used in the stakeholder analysis. So it is a power interest grid. So we try to classify the different stakeholders of our value chain in function of their power and their interest. So in the section A, you can see that these are the stakeholders that we have to manage closely, that we need to keep informed, that we need to stay involved in the implementation of the project. And in the section B, these are the stakeholders that we need to just keep informed, let's say. And this is a quick table on the stakeholder social assessment risk with the top 10 social areas where social concerns have higher risk for the whole value chain. So basically, we can see that we have very low risks with the mean on the right, and this is good for the project. And we did the same thing for the opportunities. And we can see that we have some really nice opportunity, for example, in the employment area. Quickly, the conclusion and recommendation, we can see that we have some really encouraging results concerning the environmental and socio-economic perspective of our project. We have to keep in mind that this is still a prototype that will be further optimized, of course, in the coming years. And that's it. I think. Sorry, Alinda. Thank you. So just one point I think which is important to highlight. This is the production capacity that we need to increase if we want to have better results concerning the economic assessments. And yes, thank you. Sorry if I...
Thank you, Leo. Thank you for the presentation. Sorry for pushing the time.
No, it's okay. It's okay. Thank
but
you.
That is my choice. Thank you, Leo.
Thank you.
Thank you. I think we move on with the program. You will get the slides, all of you, afterwards also, and you can, because there was a lot of data and a lot of information and figures Leo had put together. So you will definitely get the slides afterwards. We move on, and actually our next presenter will be online. So hello, Robert. Nice to see you. Nice to see you. Welcome. Can you hear us?
Yes. Good morning to everyone. Can you hear me well?
Yes, we can. And Robert Sekula is from Hitachi Energy Research, and he's going to talk about the electrical insulation about us. So welcome, and the stage is yours.
Thank you very much, Alina. I will start my presentation. Once more, good morning to everyone. My name is Robert Sekula, and I am Senior Principal Scientist at Hitachi Energy Research Center in Kraków, Poland. First, I would like to explain why we have two logos on this introductory slide. So you can see both ABB and Hitachi. And before joining Hitachi Energy Research, I spent more than 20 years working at ABB Hitachi, at ABB Corporate Research Center in Kraków, and we were initiator of that project. But in meantime, it happened something like 2 years ago. ABB decided to sell one of the big divisions, namely Power Grids division, including transformer business, to Hitachi. And in parallel, also our global research organization has been split. And now I'm working in this global Hitachi Energy Research. And this is the reason. And today I would like to talk about our experience as a final user. That this, let's say, application is related with the insulation components for power transformers. And before we will go to the main topic, you know that power transformers are very, very important components in entire power grid networks. And very often you could see these huge transformers, size even like large room. So the safety, reliability, and also lifetime of the operation for such transformers is very, very important for the grid operators. Cellulose-based insulation is one of the most important components in transformer design, and it must fulfill a lot of different functions like electrical, mechanical, thermal, and also a very long lifetime. If we have some problems with the insulation quality, I mean some voids or maybe some metallic inclusions, this is disaster for the whole transformer. I mentioned that electrical insulation, such properties like electrical breakdown strength, very low partial discharges possibilities, and dielectrical constants and dielectric loss, we call this Tangens delta, are very important, crucial dielectric parameters which must be fulfilled by transformer insulation. In addition to that, we have all these mechanical aspects, so compression strength, but also tensile strength, and also thermal, let's say, resistance is also essential, because usually transformer is working under elevated temperatures, sometimes even up to 140 centigrade. I mentioned this already, that this long lifetime is highly appreciated. There are transformers working for more than 30 years. So these are the expectations from our customers. So you see how important is good quality of the insulation to fulfill this kind of the tough market requirements. We have a lot of geometries possible, also sizes varying from few centimeters up to even meters. So on the next slide, you can see some examples of the transformer insulations, and some of the shapes are very simple, but also we have some kind of the complex shapes. And this is why we were thinking that additive manufacturing could be good opportunity for this kind of the applications. It was already mentioned in few of previous presentations that why we wanted to think about new material, steel cellulose-based material, because they are mostly used in the transformer insulation applications. It was mentioned that the current manufacturing process consists of number of the stages, and these stages are labor intensive, and there are number of the operations required to really produce this kind of the final insulation components. Usually we are using the wet cellulose pulp, and there are dedicated molds, and we sculpture on the mold the final shape. All this is many hours of manual operations to really sculpture these thin thickness shapes on such molds. After this deposition of the mold, of course, we have to use additional clamping system to remove the moisture from the wet pulp. And after that, we have another very long-lasting process and also energy-consuming. Namely, we have to put the component to the drying oven. And usually you need 5, even up to 8 hours to evacuate the moisture from such system. So altogether, we have, if you add all these stages, we have long cycle time and a lot of energy consumed. So we have number of the drawbacks, but still this is the dominant technology because it's well proved and is well known in our industry. But of course, we had idea how to change this complex process and how to eliminate some of the operations, for instance, the manufacturing and design of the dedicated mold, and also remove these energy consuming drying operations. And our idea was to use 3D printing. Also, we were considering in the initial phase of the project this thermoforming. And as it was mentioned by Heli, we just had this idea some years ago, and we contacted VTT, and the project was created aiming development of new material formulations, still cellulose based, and also new manufacturing technology. And of course, during the project execution, dozens of the materials have been developed by VTT. I think that it was close to 50 different material formulations. And of course, our key task together with our colleagues from the Insulation Kit Center, but also with the university partners of University of Science and Technology here in Krakow, it was necessary to really test these materials. And we had a quite long and extensive testing procedure or procedures for selection of the best materials. Of course, first key parameters, we call this oil compatibility. We must be sure that the material which is immersed in transformer oil and under elevated temperature, it doesn't destroy, so we don't have any mechanical issues and cracking and so on. And also, we don't have any chemical interactions between this new material and also with transformer oil. Also, a lot of mechanical parameters have been measured, so we are talking mainly about tensile strengths and also this compression strength, and number of dielectrical parameters like volume resistivity, this is dissipation factor and permeability, breakdown strength, and also the possibility of the creation of the partial discharges. And all these advanced measurements, as mentioned before, have been done by our university partner. And after testing of so many material formulations, we approach the stage that we are almost fulfilling all requirements related with the application of such materials in transformer insulation applications. What is our last task? And this is ongoing work. The final deliverable from our project is comparison of traditionally manufactured component. You can see on the top picture, this is the one of the benchmark product produced by our traditional wet pulp technology in our Insulation Kit Center in Hitachi Energy. And on the bottom, you can see the component printed by Brintner. And now our university partners, they are doing these comparative tests, aiming the final validation of the technology. So not only material, but also printing quality for our applications. Here, I would like to mention one aspect because it was questioned from the audience regarding the surface finishing. In our case, it's not so tricky. The surface of the traditional manufacturing is very close to the surface which we have in printing process. Instead of the summary, I will show you some preliminary key benefits or results we already obtained. So you can see that if we compare the labor time, so in this new printing technology, we have only few hours process. In reality, it's between 20 to 30 hours. We can reduce material waste by something like 50%, and also energy consumption, mainly due to the fact that we don't need the drying, long-lasting drying, also can be reduced by factor of 2. So thank you very much. If you have any additional questions, I am open for that.
Thank you, Robert. I was trying to give you a hint that we are running out of time, but
Yes,
you
yes,
were so
I know,
enthusiastic.
I know.
Thank you for the presentation. Robert, would it be okay if someone has a question, so they can directly contact you or through Heli and us also, and
Yes.
continue the discussion?
Yes, of course. Don't worry. I know that you have
I have a tough
strike,
task.
time, and it's not problem. If you have any questions, please contact me directly. Or you have also colleagues from university.
Yes, they are here. I
They
think
are
they are
here, so
sitting
you
in the
can also
room.
discuss some technical details with them.
Yes. Thank you, Robert. Thank you.
Thank you very much. Have a nice rest of the day.
Thank you. Okay. We move on to the next presentation now. I will switch the slides and I welcome Jami Kuusisto from Meyer Turku to the stage, and he's going to talk about the marine industry's point of view about Novum. Welcome, Jami.
Thank you, Alina. This is on? Yep. Excellent. Hello, everybody. My name is Jami Kuusisto. I'm a product development engineer in Meyer Turku. We are a shipyard based here in Turku. And yeah, we are one of the end users in this NOVUM project. So if we talk about the marine use case a little bit, these cruise vessels that we specialize in, they are hundreds of meters long, and they have hundreds of thousands of square meters of these different decorative or surfaces in them, and these are like walls, ceilings, floors, whatever, if it's there, yeah. But our core business is the hull, the design. We subcontract these areas, this furniture, these panels, and therefore it is extremely important for us to develop these use cases together with the marine cluster and with our subcontractors, so that we can respond to the need of more sustainable materials and new demands of complex architectural and visual features, and the materials that they are used that tell the story. This is also important to our customers. Most of these panels are not really suitable for 3D printing. They are flat and they are easy to produce traditionally. But there are some that are very, very labor intensive or costly to, for example, CNC out of. Here are some example pictures of the interiors to give you some perspective. There are tens of bars and restaurants inside this ship, and these are just the tip of the iceberg. There can be much larger use cases, scaling up to 10 meters or more than 10 meters, where you can actually start to maybe think about some weight reduction benefits. But of course, we are not trying to make a lightweight ship out of 3D printing. It's not there yet, and probably never will be. But in Novum, we examine these panels and their benefits if we do it with 3D printing with these thermoplastic composites, and as Leo mentioned, found out some cost effectiveness in unique structures and these very small batches. And also with the pilot line, we can make use of these built-in interfaces and post-processing methods to increase or make these first 3D printed samples into much more representative of the end use samples. So maybe some coating or something like that needed afterwards, but then it's all good. I'll only gloss over the environmental benefits. It's a multifaceted subject. The molds, as Leo explained, might be very environmentally unfriendly. I'm not saying they are environmentally unfriendly, but they can produce much emissions. So if the molds are used only 1 or 2 times, then there's a real benefit to be had here. And of course, the material, as Kinga also mentioned, is recyclable. So basically chuck it in the recycling grinder and start extruding again. So there are potentials in there. So about the marine concepts in Novum, we prepared these proof of concept demonstration pieces of this bar, facade, and pillar, which utilize also the building capabilities of the pilot line to move them around and to post-process it. Because there are post-processing methods for smaller parts, for smaller 3D printed parts on the market right now. But for these larger parts, it is quite difficult. You basically left with the option of chuck it in a large CNC or elbow grease. So for the 3D printing, we of course want to reduce the machine time and build as fast as possible, but that leads to a reduction in resolution and the details, therefore, and also the surface roughness. Well, in some cases it might be acceptable, in some cases it might not be. So in the pilot line, if we are printing a finger-sized bead of the extrusion material, then we can't have millimeter details. So this is where the pilot line comes in. It post-processes the surface for these ship parts, and then it also enables us to, for example, in the future, design more flexible installation and assembly solutions. For example, snap-on fittings or whatever your mind can think of to speed the installation and reduce the manual labor, especially on the ship where it's very time-consuming to do any labor. But this is only the geometrical side of the coin. Then we also have the longevity. So if these panels cannot last to their full life cycle, the environmental and cost benefits are lost. And therefore, in Novum, we have been conducting material tests to see how they age and how they fare in these harsh marine environments. Because if you work in marine industry, you probably know this without me telling that, but there are very strict fire regulations inside these ships. And these materials, these cellulose-based materials, currently are not fire resistant, and therefore they have limited indoor use cases. So they are much more subject to the outside environment. And this is still ongoing, and I hope some good results will arise from those tests also. And now, we are not alone in this development. I'm glad that there are huge interest in marine industry, in additive manufacturing. The concrete cases are starting to pop up, and I'm very glad of it. And also in this panel manufacturing. spaces. Lastly, about the future, I invite you all to consider this project in the context of the shipyard's sustainability strategy. We are committed to having a buildable carbon neutral cruise ship concepts by 2025, and we want to be carbon neutral as a shipyard by 2030. And it includes a lot of different things that need to be taken care of and need to be developed, but these new materials are one of them. Even though the bulk of shipbuilding emissions come from the steel structures, these materials are still needed, and we will continue the development of these additive manufacturing cases even further. And we also want to encourage and hopefully inspire everyone in the marine cluster and our subcontractors to experiment and see where these new technologies might lead us as a whole. Maybe we will get some innovations that reshape the marine industry, but for now, I guess well, small steps need to be taken to start a great journey. So I thank you all for being here and for your time, for listening to me, and thank you.
Thank you, Jami. Jami, thank you for the presentation and actual kind invitation to further work with you, that your interest is to continue, and you have great aims for the company to move forward. I see at the clock, so we can continue the discussion over lunch, and definitely you can contact Jami directly as well. So we move on to the next presenter. He's going to present online. So welcome, Luca Chili from CRF. How do you pronounce CRF? Is the
CRF, so from,
yes. So from the automotive or car industry part. So the floor is yours, Luca.
Thanks. Hello, everybody, and sorry to not be there in person, but anyway, I'm here. And today I will go to present some of the sustainable strategies that we have in automotive related to the plastic materials, both bio-based and recycled materials. I'm Luca Giri from CRF, which is Centro Ricerche Fiat, and I'm part of the materials engineering team in Italy, and I'm a plastic specialist. So during the presentation, I will go through these main topics. So what are the sustainability drivers for the material selection? What are the bio-based materials, the recycled materials, and the conclusions. So the sustainability drivers for material selection. Automotive sustainability passes through development of new car concept, architecture, and systems, but also through the adoption of new materials, leading to a beneficial environmental impact. So, in order to have a green content, it's mandatory to couple the material criteria selection with the final requested performance. So, in other words, if you want a green materials, you have also to take in mind the final properties that the components need. These are the two main strategies to increase the green material content in the auto. I'm talking always about plastics. So use biopolymers and biofillers and increase the use of recycled materials. So what are bio-based materials in automotive? In automotive, there are two different bio-based materials, the biocomposites and biopolymers. Biocomposites are materials in which the reinforcement is natural fibers like hemp, kenna, flax, and so on. And the matrix could be both from fossil or renewable resources. Indeed, biopolymers is a materials that derives from renewable resources, usually from feed scraps. Use of this type of materials lead to a reduction of the carbon footprint. So we have a saving of fossil resources and also lead to a potential weight and cost reduction. I will show you some current application about the bio-based material, biocomposite materials. So this is an example. It's a current application on Alfa Romeo Giulia. This is the dashboard carriers. It's a biocomposite structural application in which we have a polypropylene reinforced with hemp fibers. And this solution also led to a weight saving compared to the standard application, which is with glass fiber or talc that are with higher density than the hemp fibers. In this other chart, I report indeed an aesthetical application. This is the fascia of the Fiat Panda. It's a 2K injection in which the aesthetical layer is made by polypropylene with wood fibers. In this case, the wood fibers are aesthetics. The other way to use bio-based material is the biopolymers materials. In this case, I show you an example. We have a polycarbonate bio-based, which is partially derived from starch. This materials has comparable mechanical properties to the virgin one, but shows higher chemical and really high abrasion resistance with high aesthetic appearance, great colorability, and high UV resistance. And for this reason, we have been able to apply it in several interior applications, such as these lenses of the climate control of Fiat Tipo, Fiat Ducato. We use it also for the key cover of the new 500 electric, and also for a small trim around the 500L radio, this ring. It's a piano black effect. New development. Now I'm talking about the NOVUM project. So we arrived in the NOVUM project in the last year. So it was already developed, and we evaluate two of the many compounds that the consortium produced during the 2 years before. We choose the 32 and 33 compounds, and we started the evaluation on the injection molding technologies. We saw that they show similar properties to polypropylene talc, and for this reason, we tried to mold it on an existing mold of the Jeep Renegade center console. And we have a really good results because we see a really good processability in the mold and also good aesthetics. As you can see in the photo, we inject really good parts. Then, of course, we are also interested in the additive manufacturing technologies, because for spare part can be a winning point, sometimes the additive manufacturing, and also it can lead to lower cost during the development phases, and can be also feasible when you have a low or medium volume part production. So for this reason, the next steps will be to evaluate the properties of the fascia of the 500 dashboard, which is a really customized color component that we have in the interior of this car. And so couple the additive manufacturing technology with the green material content can be a really good winning point to have a really high customized application. The other way to increase the green materials is the use of recycled materials. Recycled materials are from different chains, which are post-industrial scraps, post-consumer scraps, internal scraps, and end-of-life plastic parts. So in the graph here, I report with what is more or less the plastic share in the automotive, where up to 100 kilograms of plastics per vehicle, we have more or less the 50% covered by polyolefin, like polypropylene and polyethylene. And then with polyamide and the styrolic alloy, so polycarbonate and polycarbonate ABS, we are around 90% of the total plastic share, thermoplastic share in the car. So for these reasons, in the last 1-2 years, we homologate a different thermoplastic recycled materials, polypropylene, polyamide, and PCABS, because with these 3 classes, we can cover more or less the 90% share of the thermoplastics. And of course, to increase the use of recycled plastic share in the future cars, there is also a need of stable performances of the materials, the new material specification that now I show you, and also new specific design, because with the recycled materials, you have different mechanical properties, and so you have to apply these different mechanical properties on the final component.
Luca, can you hear me? Just
Yes.
the time is running a little bit, so
It's basically finished. This is just an example of some mechanical recycled component. This is polypropylene on the Jeep Renegade. I go fast. This is polyamide on the front module of the 500 electric. This is PCABS on an interior component, always Jeep Renegade. These are just examples of some current application. And the new development will be the chemical recycling. When the mechanical recycling is not possible, the chemical recycling can be a winning point, because you have this, then say mechanical, physical, mechanical properties as the virgin one. So in conclusion, the major drivers for recycling development are regulation for homologation and new EU strategies for plastics in a circular economy. Green materials are already present in vehicles, and several innovation projects are running to improve our product sustainability, like NOVUM. Next generation models will introduce most innovative materials, and to have an innovation output, you need a reliable application. And collaborative research and innovation activities are crucial to speed up the readiness of sustainable materials, strengthening value chain. So thank you all, and sorry if I go longer.
No, this is just it's like
I speed up a bit.
No problem. It's like an avalanche. Once we're a little bit late, and so you were unfortunately the last online as a presenter. So, thank you, Luca, for the presentation. It sounds very interesting, and I see a little. It's a radical change you're facing with the material use in the car industry as well, in the material wise, but also production wise. So thank you for sharing your insights, and I see that for you also there's going to be a continuation in the path, obviously. Yes.
Thank you.
Thank you, Lucas. So I think I'm looking at the time, and we have heard all the presenters now present their slides and so on. And I think the next step would be sort of have a wrap-up discussion. And I invite Heli Kangas, the project coordinator, to the stage as well. And please, I will move here so people can see you online as well. So, Heli, what's next? That's what we are going to talk about, and let's take first the cellulose-based material, the novel material that we call now. So, how do you see the future, and what are the next steps for the material?
Well, I'm personally and at VTT we are ready to go commercial with it, and for that we obviously need a commercial partner to take it to the market. So we are open for any kind of suggestions and collaboration possibilities in order to do that. And we see this novel material, which has been developed it's a base material basically. So because there are various end-use cases, and they all have the different requirements. So I think it would be then to tune the material, you would need the kind of feedback from the end-use industries, and then we would do it together. But I see it as a very versatile material, and even though, like Jami mentioned, that this is not fireproof, but I had a discussion during breakfast with Kirsi today, and she said, like, we are nearly there. So it's not that there are not any fireproofing properties, but you need to optimize them, obviously. But I think that the concept is ready to be taken into commercial.
Okay, so we have moved quite a lot during the project with the material development. Let's take the 3D printing, and we now have a quite large-scale 3D printer developed, and we have the pilot line, but let's take the 3D printer.
Yeah.
So what next?
Well, I think that was summarized by Tommy quite well. I mean, how many visions did you have? 4, and that's not even, that's a start. But, combining, I think there was the multi-material, like you see in here, something like that. And then hybrid was the keyword, combining 3D printing with injection molding and using the same post-processing line for that. So I think there are multiple kind of further development possibilities. And again here, I think it's good that we have projects to continue the development, but of course then these commercial operators are, so to say, asked to hop on board and develop these with us. So, but I think this have been a very good collaboration, and where we started desktop printer and then moved forward towards this very large scale printer. I think in 4.5 years, I mean that's an achievement and accomplishment, and I think we need to give kudos to us as well to accomplishing that. So I'm very happy about the development, and Tommy is there, wiping his forehead. So it's been, kind of sometimes stressful 4.5 years, and the COVID and everything on top of that. But we've managed, and I'm very proud of the accomplishment. And I think there is a clear roadmap and a path forward to go further with this. And you saw Jami's, for example, this carbon neutral shipbuilding, carbon neutral shipyard. So I think this is a good start towards that.
A lot of opportunities. Any last words, Heli? At this point, I'm nearly closing the event or the streaming session. So
I think that this whole event has been like a summary of the project, but I still encourage someone who's interested in commercializing the material to contact us and also contact Tommy or myself if there is an interest or when there is an interest to co-develop the printing and post-processing.
Okay, thank you, Heli. This was excellent and exciting to be present face to face, and thank you all those people who are online as well. I will now close our event, and I thank you all for participation. So thank you all for coming.
Thank you.